Okay, let's get started. The second lecture. The next speaker will be Professor Michael Harris of Institut de Mathématiques de Seoul, France. And briefly introduce his career. He got PhD from Harvard. And he's going to deliver on the talk about automorphic Galois representations and the cohomology of the Shimura varieties. Okay.
Thank you. So I didn't realize this was going to happen, but Jim Arthur explained what I'm going to be talking about. He explained how conjecturally one of the parts of the language. Oh yes. So one of the important components of the language program is the identification of representations of Galois groups with automorphic representations. And specifically, he talked about the Artin conjecture. Very little is known about the Artin conjecture, although it's considerably more than was 10 years ago. Two-dimensional representations. But there are other situations where one can say quite a lot about Galois representations using the cohomology Shimura varieties. I'm going to say more or less what seems to be the limits of this at present. So K is going to be a number field, gamma K is an absolute Galois group. And rho is going to denote an L-adic Galois representation, n-dimensional. And the advantage of using L-adic numbers rather than the complexes is that there's a lot more room for to reflect the total discontinuity of the Galois group. Let's suppose that V is a finite place of K prime to L. Then the local Langlands correspondence associates to the restriction of rho to a local decomposition group an irreducible, generally infinite dimensional representation of GLN of this local field. So that's the local Langlands correspondence. This is the local version of what Jim was talking about. And these are one can think of this as a collection of signatures, or one signature with infinitely many prime factors attached to this n-dimensional Galois representation. So now what can one do with these objects? I already told you that V is prime to L. I need to put together an automorphic representation, which is a collection of such representations of the local group, but for every place. And L-adic Hodge theory, which is what Matt was talking about yesterday, except it was P-adic Hodge theory, gives you a formula, gives you a candidate, just an infinite dimensional representation locally, either at Archimedes Euler complex prime or at prime dividing L. And so now for every place of the field K, we get a representation. And the reciprocity conjecture says that when this representation we started with is reasonable, then it should be coming from an automorphic representation. So let's see. I want rho to be irreducible. So suppose rho is irreducible and geometric. Geometric was this condition in the middle here, this geometric condition. And then it's unramified outside the finite set. And then you put these things together. This is a technical condition I want to talk about. You tensor them all together. I didn't write that down. So you tensor. This is the tensor product, the restricted tensor product over all of these, and then it occurs in the L2. In fact, in the cusp forms on this locally symmetric space. So that's the reciprocity conjecture, part A. Starting with the Galois representation, you can put together prime by prime an automorphic representation, a cusp form. This is part of Langlands program. And in the other direction, suppose you start with a cuspal automorphic representation. And suppose at each place there's the local representation, every Archimedean place satisfies this technical condition. For example, cohomological representation. Then one can get an n-dimensional geometric Galois representation. So with this same property. So this is a, in other words, this 1 minus n over 2 is again a technical factor that has to do with normalizations. It's not interesting. The point is that the representation one put together from the Galois representation is the representation, the automorphic representation one started with. So these are, in other words, if you put these classifications, I think that Matt called them certain and uncertain. So if you put these restrictive conditions on the Galois representation on the one hand and on the automorphic representation on the other hand, then they give you the same object, and they can be indexed, as in Jimar's talk, by L functions. But that's I'm not going to be talking about that. Now, actually, one can prove this in some sense. So that's my main topic. Suppose K is either a totally real field or a totally imaginary quadratic extension, and suppose pi is a customizable automorphic representation. Now, suppose it not only satisfies this algebraicity condition that I didn't define, but it actually satisfies a stronger version, which can be said that the automorphic representation occurs in the cohomology of some locally symmetric space. So suppose you have such a thing. And I'm going to add another hypothesis. This is, suppose pi is polarized, which is to say, well, if it's a CM field, that means its dual is isomorphic to the image under complex conjugation. And if it's totally real, then its dual is basically the same as pi, except that you can twist by a Hecke character. So we have these algebraic representation, regular representation, and polarized. So first theorem. Without the polarization condition, there is, in fact, the Galois representation that was predicted by part B of the conjecture, with some, what can I say? I can't say that it's irreducible. All I can say is that it's a unique semi-simple Galois representation. And there is some, what does this say? This says that the local factors correspond, except possibly a prime dividing L. More, suppose it's polarized. Then there is, in fact, a compatible family of n-dimensional semi-simple representations that satisfy the full correspondence at all primes. And in particular, it's known that rho is Duram, that is to say, it's geometric. At all primes dividing L. All right, so this is the state of the art as of at least the time a few weeks ago when this was written. It may have been improved slightly since then. Okay. So part B was proved by many people over many years. I was asked to do some of the names. So for n equals 2, there's already this very long list. But that ended about, well, Takeshi Saito's contributions about almost 20 years ago. And for general n, here's the list of names, and starting about 25 years ago. And to which one should add everybody who's responsible for the fundamental lemma, because without the fundamental lemma, none of this would be possible for n bigger than 2. And all right, so there's a list of names, also in the printed paper. So what's more is that one has more information about the representations. That is to say, the representations are either actually cohomology of something, so I use the word motivic to say that they are part of the cohomology of an algebraic variety, specifically the Shimura varieties attached to unitary groups, or they are nearly motivic in the sense that if you do some simple tensor operation, they become motivics. For n equals 2, you have to take a symmetric square, or n is bigger than 2, you can take an exterior square. So in particular, they can all be studied directly by cohomological methods, and cohomological methods are what give the construction of the representation in the first place. And how is that done? Well, this broadly follows the outline developed by Langlands and Kottwitz over this 20-year period. Namely, the Arthur Selberg phase formula, on the one hand, is a way of characterizing all the automorphic representations, and the Galois phase formula calculates the Galois representations on cohomology, and putting these two things together, you see that they have the same terms roughly, and so you can see that the cohomology of the Shimura variety is a sum of Galois representations with this local property. Now, as for representations in A, they are not known to be motivic, and this is an open problem. So these were first constructed in joint work that has yet to appear with Lannon, Taylor, and Thorne, using not the kind of cohomology that is necessarily motivic, but using rigid cohomology, rigid analytic subvarieties of Shimura varieties. Very soon before after the results were announced, Peter Schulze gave a completely different construction based on the perfectoid structure of Shimura varieties, an infinite level, and I suppose he'll be saying something about that. But what they have in common is that they, from the point of view of the Galois representations, you start with the motivic representations, or the ones that are nearly motivic, as I said, the ones in part B, and then you somehow patch them together by p-adic interpolation. And because in case A, the p-adic interpolation loses all sight of the geometry, the cohomology of projective varieties, there are no prospects. Again, one shouldn't speak too soon, but at least I haven't heard of anything that's going to be announced before the end of this conference. So, as far as the local-global compatibility has placed in that reduction, I should mention Ila Varma's thesis. Ila Varma is a student of Richard Taylor, and there's more work in progress. All right, so these are the representations. So that's going in one direction, starting from the automorphic representations, constructing Galois representations. That is, in some sense, the easy direction because it's constructive. You can look at the cohomology of something and then count points, or do stuff one way or another, use cohomological properties to study the Galois representation. But here, this is the other direction. So which of it represents automorphic? Which Galois representations do you get? The question: which Galois representations come from this construction? Well, this is a version of the Fontaine-Mazer conjecture, which is Galois theoretic version of the Langlands program. So suppose a p-adic Galois representation. Remember, we still have this global Galois group is HT regular HT for Hodge-Tate. If at every prime, notice that will become P. So a p-adic Galois representation, this is true, phase transition. If at every prime dividing P, the restriction to the decomposition group is de Rham, that's one of those unnamed properties of Galois representations with Hodge-Tate weight spaces of dimension at most 1. So this is a very technical condition that is, as you may or may not anticipate, is precisely paired with the technical condition on automorphic representations. The conjecture is that all of the representations with this property come up this way. So, that is to say, this is a n-dimensional, I suppose it's the most natural n-dimensional generalization of a conjecture on modularity of elliptic curves, whose name seems still to be undetermined, so I'll just leave that. So any row with, so this is in other words, there is a relatively simple characterization, conjectural characterization of all the representations that one gets this in this way, in the first part. Now how does this, so this is a regular case. So the regularity condition can be relaxed slightly. So I said that the Hodge-Tate weight spaces had to be of dimension at most 1, but this can be relaxed slightly. So let me give you an example. An elliptic curve has 2 Hodge-Tate. It's the cohomology has dimension 2. It has 2 Hodge-Tate weight spaces, each of degree dimension 1. A 2-dimensional representation, complex representation of the Galois group, Q bar over Q, has 1 Hodge-Tate weight space of dimension 2. That is, and in general, an abelian variety genus G has 2 Hodge-Tate weight spaces, each of dimension G. So this work of Goldring and Stroh, at least in principle, would allow you to say something about the Galois representations on cohomology of abelian varieties of genus 2. But that's it. That's the wall. There are no, again, something is in the air. There's no way to use Shimura varieties to construct Galois representations systematically. Although they must be there. For example, abelian threefolds over Q cannot be proved modular in this way. Now I should say something. The Galois representations without this hypothesis should be in a completed cohomology that Matt talked about yesterday, but you can't see how to get from that to automorphic forms, and therefore there's no known way to connect that to the alignments projections. Similarly, base fields that are neither totally real nor CM are presently out of reach, and you can find a cubic equation that is neither, gives you a fail that's neither real nor CM, and then you're out of luck. There are also some mostly unpublished results for groups other than GLN, so that's, for example, symplectic groups, there are some results. Some published and some unpublished. All right. So now, how does one go about proving anything in the direction of this conjecture? So we have the construction in one direction, how can we go back? Well, this is so now we're going to introduce the totally real subfield. Somehow it's become analytic again. These have their different bases. So now we suppose that we can assume that that rho takes values in GLN of some L-adic integer ring O with maximal ideal M and residue field K. And let's suppose that the Galois, so then we can reduce it mod maximal ideal. And let's say that the rho is residually automorphic if it's congruent modulo M to one of these that were constructed earlier. So here is the most complete general result in the direction of the reciprocity conjecture. It was, I'm not sure whether it's out, it's either in the annals or I think it's in the annals. This is due to Barnett, Lamb, G, Garrity, and Taylor. It was proved in around 2010. There are a lot of technical conditions that can presumably be improved. Suppose L is bigger than twice n plus 1. Suppose K does not contain a primitive alternative unity. Suppose that rho has this self-duality condition in this technical sense. But yeah, so here I've combined the totally real and so there's no mu if K is CM, and there is no C if K is totally real. So that's one formula for both. Suppose the restriction of rho bar, that's this reduction in mod, the maximal ideal, is absolutely irreducible, not just the representation itself, the restriction to this cyclotomic extension. And for any prime dividing the restriction, dividing L, the restriction to the decomposition group is potentially diagonalizable and Hodge-Tate regular. This is a even more technical condition, but it's all in the framework of p-adic and L-adic Hodge theory. And finally, suppose that it is residually automorphic. Then it's automorphic. So this is the last, well, it's not the last version, but it's the strongest version, at least in the setting we're talking about, of the series of theorems that began with the work of Wiles on Fermat's theorem. So the two-dimensional case was this theorem is the Taylor-Wiles theorem. The method builds on earlier work, which gave less complete results with Closell and Taylor. Kissin's construction of semi-stable deformation rings, Taylor's theory of level raising, and the tensor product trick. So one thing about potentially diagonalizable is that it contains something that's familiar. It includes all ordinary crystalline representations and all, this is just, again, p-adic or l-adic Hodge theory, but it's much more flexible. It was the notion that allowed them to go beyond what people thought possible. Now, this is still still an active area. So Talagari and Garrity and also David Hansen have a different approach using deformations of perfect complexes that applies in more general situations, but this is still undergoing refinement, so I wouldn't make a statement now. It should be able to improve on the kinds of representations that can be treated. So there were a number of properties. So one is this corresponds to part B of the modularity of the construction of Galois representations. 2 is some sort of unfortunate restriction that may eventually be removed. 3 includes most familiar types of representations. 4 is a real obstacle. How do you know? So remember, we were originally interested in characterizing all representations that came from automorphic forms. I haven't explained why you care that a representation might come from automorphic form, but that's for later. What apart from satisfaction in knowing that the conjectures are true, why would you care? But this is something that seems to be a very strong condition. It is, in fact. Well, in fact, this L-adic row is residually automorphic. That's a condition on one L. If you have a whole family compatible system with the same, what does it mean for the system compatible? Basically, it means it has the same signature in the sense of Jim Arthur's talk. That is to say, the L functions are the same. Look at almost all primes. So if you have a member of a compatible family of L'-adic representations, if one of them is known to be residually automorphic, then you don't care about your original L, it comes along for free. So what do you need to know? You need to know that there's a motive M such that the L-adic representation attached to the motive, I haven't said what that is, but say a motive. So a motive, this gives you an n-dimensional Galois. A motive is a complicated geometric structure that has a whole lot of cohomology groups, including one for each L that gives you an L-adic Galois representation. Suppose that your row Lm is congruent to, your row is congruent to the L-adic representation attached to the motive, on the one hand, and on the other hand, it's known a priori to be residually automorphic for some different prime. So then, if you know that, then you can apply, and assuming the various other hypotheses that L and L prime, L and L1 are both bigger than 2n plus 1, and so on, you can apply the modularity lifting theorem and you can get modularity of your original row. Okay? Well, you can't always do that. But suppose rho is potentially automorphic, that is to say, it becomes automorphic after a base change to a Galois extension at the appropriate time. Then by an argument by an argument using Brouwer's theorem, this implies that LS rho is meromorphic and has no zeros at the edge of the critical strip. And thus, all you care about is this property, that the L function is meromorphic and has no zeros at the edge of the critical strip, then all you need to know that there's a motive M over K prime with the properties that I mentioned in the last slide. Okay, well this seems pretty obscure, but in fact there is a large supply of such motives that was provided by physicists, actually, or physicists gave reason to care about these things. You can, here they are. So you take these n-1 dimensional hypersurfaces in Pn with this equation. There's a parameter t here, that is a one-dimensional family of this. This is just like a deformation of the Fermat hypersurface. And the degree n+1 guarantees that the hypersurface is Calabi-Yau, and therefore it attracted the attention of physicists, and therefore there was some knowledge of these structures. And it's known that the monodromy of this infinite dimensional family, so it's known thanks to work of a number of people, Katz in particular, that the monodromy of this family is full symplectic or orthogonal mod L1 for almost all L1. In fact, stronger result. So this was applied to potential. So I should say the method of potential automorphy was introduced by Taylor just about 15 years ago to prove the new cases of this property, the meromorphy of L function of elliptic curves over real quadratic fields and other real fields and some other two-dimensional representations. So this was applied in a number of papers, and let me just give a consequence. So here, this theorem improves on recent work, a recent result with Cozell, Shepherd, Barron, and Taylor. So let S be an elliptic modular new form of weight K for some gamma 0n. There's a version for gamma 1 of that. For any prime not dividing n, let AP of F denote the eigenvalue of the normalized Hecken operator T, and let's normalize it so that it falls. We denormalize it so that it falls in the interval -1, 1, and then as P varies, these normalized eigenvalues are distributed in -1, 1 for the measure square root of 1 minus t squared dt. So this is a subtlety conjecture for elliptic modular forms, which is only one of a vast collection of subtlety conjectures for every kind of geometric Galois representation. But these are the only ones, two-dimensional ones, the only ones for which one has any hope of saying anything. So in particular, if you use an elliptic curve over Q, then AP and 1 plus P minus, so this AP, this eigenvalue, elliptic curve over Q is known thanks to Roy, Conrad, Diamond, and Taylor that it comes from a modular form of weight 2. Then this AP of E is this AP of the modular form. Then these numbers are equidistributed for this subtlety. So the fact that it's gamma 0 then it just makes the statement easier. So what the subtlety conjecture, of course, is a red herring. What one really proves, it was some in the 60s, Tate and Serre showed that the subtlety conjecture for elliptic curves was a consequence of the meromorphy of symmetric power L functions and the non-vanishing along the the right-hand boundary of the critical strip. So that's a good proof. And avergence was proof for Hilbert modular forms by Barnett, Lamb, and Jean Garrity. So in the few minutes remaining, here's another. This is the last theorem in this set. So here's the strongest result. to date in the direction of the reciprocity conjecture for Hodge-Tate regular motives over a number of fields. This is a recent work of Patricus and Taylor. So K, as always, totally real or CM, and we have a weakly compatible family of lambda-adic representation. So now we have not just one L-adic representation, we have to have a compatible family. For example, the cohomology of a motive, so this, I can say, n-dimensional representation, so rank n is the coefficient field. Assume they are all pure of the same weight and they are Hodge-Tate regular and then they satisfy whatever is the appropriate polarization condition. Then the whole family becomes automorphic over some finite totally real Galois representation. Actually, it doesn't, not just only one finite totally real Galois extension. In fact, there are infinitely many, and they can be as far as you like from any. This is always. Thank you. So this is actually quite strong. This says that if you happen to find a rank n motive whose cohomology has this regularity property over a totally real or CM field, then you know that its L function is meromorphic and non-vanishing along the line, and if it comes from an automorphic representation. So that's the strongest. Now, there aren't that many examples of what motives that occur naturally. We can construct them artificially. For example, this Hodge-Tate regularity condition, if the Hodge-Tate weights are separated, for example, then Griffith's transversality says that this should be a countable set. So they shouldn't be, well, it's always a countable set, but they vary in a zero-dimensional family. So these are not the most typical kinds of Galois representations. As I said, three-dimensional abelian varieties cannot be approached by these methods. So, most of the representations discussed above are realized in the cohomology of Shimura varieties attached to unitary groups. And so you get cohomological candidates for the motive. And then you cannot generalize, one doesn't know how to generalize these conjectures to other kinds of motives. So one has to try to, since one doesn't want to quit working, one has to find something else to do with these results. And so one thing you can do is to try to study their special values, their L functions. Now you may say that this is an artificial class, if you take the point of view that these conjectures are very general, you may feel that there's an artificial class of motives to study, but on the other hand, these are the ones that come from automorphic representations, so you may as well. So the special values are related to arithmetic properties, and specifically orders of Galois cohomology groups. And automorphic methods can be used to prove partial results in the direction of these conjectures. I'm just going to give one of many possible applications. So K is always CM. Suppose V and V prime are Hermitian vector spaces over K of dimension n and n minus 1 respectively, and G and G prime are their respective unitary groups. Pi and pi prime are automorphic representations of these things. So now there's a whole other theory. It's related to what Shimura was talking about. You start with automorphic representation of unitary groups. These can give you automorphic representation of GLN. In fact, all of these results, none of the results I talked about earlier would have been possible if we only had GLN to work with for n bigger than 2. Everything is done by means of trace identities, base change identities for unitary people. And now let's do something completely different. Let's take actual functions in these automorphic representations. These automorphic representations are spaces of functions. I was not using anything about them. Let's actually take functions and integrate one against another. Then you get a number. Well, what you get is a bilinear form. And let's put in some more stuff. And now so we do with this is the function. This is the rule function. This is a kind of period. There's another rule period, and then we can divide it to make this homogeneous. And now, so we have an expression that at least is invariant under multiplication. What is this? So this is the Ichino-Ikeda conjecture, but they work with orthogonal groups as the word for unitary groups. Here is the conjecture. This period is some elementary factor times a finite product of explicit integrals times a ratio of L functions. The numerator is the central critical value, which was made popular by the conjecture of Burcham, Swinnerton, and Dyer, which corresponds to the case n equals 2 of this. That's a special case of this. Yeah, it's related to the Rosalier formula, except this is a value. And actually, amazingly enough, Wei John has actually proved this conjecture in certain cases, and he's reduced the general case to purely analytic questions. The p-adic property, that's the numerator, it's a very popular, it has the possibility, it can vanish. The denominator is an L function of adjunct of something, what's a Langlands L function. It can't vanish but it's there. And the p-adic properties turn out, so this is, I think I changed the notation. So this little pi is a representation of the unitary root, this capital Pi is a representation of GLN, and this is in fact a Langlands L function of the representation of GLN, some specific Langlands L function. Interestingly enough, these p-adic properties of this special value are related to the deformations of this Galois representation. So in fact, I haven't really got away from the original problem. And the fact that case n equals 2 is the starting point of Hilbert theory. So, since we seem to have time on our hands until somebody tells us how to treat these other motives, let's try to do Hilbert theory in higher dimensions. Well, first we have to, I said the p-adic properties, but this number is transcendental. We want to make it something algebraic. So we divide it by the mean period, and we get an algebraic number. And this is known in some generality, n equals 2 due to Shimura and recent work, in particular with Grosvenor. If you were willing to take a liberal interpretation of the Leeds conjecture, then you would send this number. Now, Heda, in the case of n equals 2 rationals, Heda found a normalization, a specific normalization of this period, such that the quotient is not only rational algebraic numbers, an algebraic integer that measures congruences between pi and other automorphic representations. And then you get back to the Taylor-Wiles by relating that to deformation. Question. So I'll conclude with a few questions. Is there a similar normalization for general N and general K that is totally real or CF? The Ikeda conjecture suggests an inductive approach. Here's a question. Given pi, does there exist pi prime such that the numerator divided by the appropriate mean period region is a p unit? I think that's a hard question. This is related to the problem of the vanishing of the Iwasawa numerator. But since we're making conjectures, are these values actually equidistributed? Is there some, can you say, in general, the proportion of pi primes in a p-adic family? You read about families of automorphic representations in the Seoul Intelligencer, in the article by Sabu Shin. Yeah, there you are. Right? Is this property equidistributed? And then another final question related to recent work of Darmon Rocha and others. Does the period admit a p-adic interpolation as f and f prime vary in a Heda family or an order convergent family? And finally, does this normalized L function admit a p-adic interpolation in Heda over convergent family? So this is related to long-standing conjecture of Maser. Oh, I thought it was finished. Okay, but my time is up, so I may as well stop. I think my time is up. Is my time up? Okay. 1 minute. Oh. Well, I mean, these are maybe I should just show you. These are the last questions. I'm not going to. Oh, yeah. This is just the left-hand side, the last question. The left-hand side remember there were local pairings, and this is somehow fixed. So if we let these functions vary, then the question: what are the p-adic properties of this? This is an open question in the p-adic language program, but it's not well formulated, so I'll leave it there.
Are there any questions and comments of this talk?
Yeah.
So the z depends on the f and the f prime and so on.
Yes.
So the question is in a way partly how the z, or maybe partly how that z varies.
So suppose you don't know how to classify representations, p-adic representations of a p-adic group, but you want to look at pairings. Suppose you think you can maybe say something about pairings. Well, it's very unlikely in general that there are going to be pairings, but maybe you can get some information by studying the growth of the pairing. And this formula says that the growth property is completely determined by that explicit integral. That's it. That's the question.
Okay. Any other questions? Okay. Then let us thank the speaker again. The next lecture will start at 5.